What's up everyone, it's Stack Lessons here. Welcome back to the channel. Today we're diving into Amazon DynamoDB for data engineers, Streams, TTL, DAX, and key design. Let's get into it. By the end of this video, you'll know exactly when DynamoDB is the right answer on the exam, and just as important, when it's the trap that costs you points. DynamoDB shows up across both the data store management and data ingestion domains, and the exam writers love using it as a distractor for analytics questions. We'll cover partition key design, streams, TTL, DEA-C, and the secondary index rules that get tested constantly. Let's start with the single most important rule for this entire topic. If a question mentions analytics, aggregations, joins, business intelligence dashboards, or ad hoc queries, DynamoDB is the wrong answer. Full stop. The exam writers know that candidates from a relational background reach for DynamoDB when they see a database question, and they exploit that instinct on almost every test. Internalize this now, and you'll save yourself several points on exam day. Here's how Amazon Web Services defines it in the developer guide. DynamoDB is a serverless, fully managed, distributed NoSQL database with single-digit millisecond performance at any scale. Every word in that sentence matters. Serverless means you never touch a node. Distributed means it shards your data across partitions automatically. And single-digit millisecond latency is the promise that makes it perfect for shopping carts, session state, and user profiles, but completely wrong for scanning millions of rows. Think of DynamoDB as a mailbox. You know the address, you grab the letter instantly. That's exactly what it does. Point lookups by key in single-digit milliseconds for things like shopping carts, sessions, and user profiles. There are no joins, no group by, no ad hoc SQL. Athena and Redshift are the opposite. They're like a library catalog where you can ask, show me all books about cooking written before 1990, grouped by author. That's what aggregations, joins, and BI dashboards need. Trying to do analytics in DynamoDB is like searching every mailbox in the city for cooking books. So when the question says analytics, your answer is Athena or Redshift, never DynamoDB. Here's the mechanism that makes everything else click. When you write an item, DynamoDB takes your partition key and runs it through a hash function. That hash determines which physical partition the item lands on, a partition A, partition B, partition C, and so on, across hundreds or thousands of partitions for a large table. Now here's the part the exam loves. Each partition has hard limits, 3,000 read capacity units and 1,000 write capacity units. If all your writes hash to the same partition, you hit those limits and get throttled, even when your table has plenty of total capacity. That's the hot partition problem in one diagram. Picture a grocery store with 200 cashiers, but everyone lines up at register number 5 because that's the one labeled today's date. The other 199 cashiers are standing idle, and your customers are furious. That's exactly what happens when you pick a low cardinality partition key like a date, a status flag, or a country code. DynamoDB has the capacity, but it's all sitting on the wrong partitions. So how do you spread the load? That's the next slide. This is straight out of the Amazon Web Services documentation, and it's the exam correct answer for hot partition questions. The bad version uses today's date as the partition key, so every write today hashes to the same partition. The good version appends a random number between 1 and 200, turning a single key into 200 logical keys. Now writes spread evenly across 200 partitions, and your throughput scales. There's a trade-off. Reads now have to query all 200 suffixes and merge the results. That's the cost of the fix, and the exam expects you to know it. One sentence from the docs gives you 3 exam-tested facts. Streams is time-ordered, meaning changes come out in the order they happened. It's item level, meaning you see each individual insert, update, and delete, not just batches. And it has 24-hour retention. Think of streams as a security camera pointed at your table. Every change is recorded with a timestamp, and after 24 hours, the tape gets overwritten. If you need longer retention, you reach for Kinesis data streams for DynamoDB instead. This is the architecture the exam expects, so memorize it. Nexer Retail has an operational DynamoDB table holding active shopping cart state. Streams captures every insert, update, and delete on that table with 24-hour retention. Lambda subscribes to the stream, transforms each change into Parquet records, and writes them to S3. From there, Athena can query the analytics-ready data directly, using the Glue data catalog as the metadata layer. That's the textbook change data capture pattern, and it's the exam-correct way to bridge an operational DynamoDB table into your analytics lake. TTL stands for time to live, and it's the free cleanup mechanism. You set a Unix epoch timestamp on each item, say 30 days from now for a session token. DynamoDB walks the table in the background and deletes anything past its expiration, and here's the magic phrase: without consuming write throughput. Think of it like printing an expiration date on milk cartons. DynamoDB checks the fridge in its spare time and tosses anything past the date for free. If the exam asks how to delete stale data at no cost, the answer is TTL. Here's the caveat that gets tested: TTL is not instant. Amazon Web Services says deletion happens within a few days of expiration, not at the exact moment the timestamp passes. So an item with a timestamp from yesterday might still be sitting in your table tomorrow. If your application needs strict accuracy, you add a filter expression to your query that excludes items past their expiration. The deletion is eventual, but the filter makes the read consistent. Remember, both have a free deletion, but not immediate. DEA-C stands for DynamoDB Accelerator, and it's an in-memory write-through cache purpose-built for DynamoDB. The headline benefit is latency. Your reads drop from single-digit milliseconds straight to microseconds, orders of magnitude faster. The next thing to know is that it's API compatible. You swap the standard DynamoDB SDK client for the DEA-C client, and your application code stays identical. And finally, DEA-C is built for read-heavy workloads. Amazon Web Services recommends a cache hit rate above 90%, because write-heavy workloads replicate every write across all DEA-C nodes and degrade performance. So when your reads dominate your writes, DEA-C is the easy win: no cache-aside logic, no invalidation handling, just a drop-in client swap that pays off immediately. This is the single most tested DEA-C detail, so lock it in now. DEA-C cannot serve strongly consistent reads. If your application sets consistent read equals true, that request bypasses the cache entirely and goes straight to DynamoDB. DEA-C only accelerates eventually consistent reads. Think of DEA-C as a post-it note stuck to the fridge. It's fast, but if someone else updates the data without telling the post-it, your answer is stale. So if a question says microsecond latency and strongly consistent in the same sentence, DEA-C is wrong. That combination doesn't exist. Here's the comparison the exam loves. On the left, DEA-C is API compatible with DynamoDB. You swap the SDK client and you're done: no code rewrites, no cache-aside logic. But it only does eventually consistent reads, and it's purpose-built for DynamoDB workloads. On the right, ElastiCache running readies or memcached is a generic key-value cache. It works with any data source, DynamoDB, RDS, an external API, anything, but you write all the cache-aside logic yourself. You decide what to cache, when to invalidate, how to serialize. The exam trigger is simple. If the question says minimal code changes to cache DynamoDB, pick DEA-C. If it says cross-database caching or generic caching layer, pick ElastiCache. Start with the baseline. A standard DynamoDB read sits around 5,000 microseconds. That's 5 milliseconds fast, but still in millisecond territory. For most web applications, that's perfectly fine. But once you're driving tens of thousands of reads per second, those milliseconds start to add up, and your tail latencies get ugly. Now add DEA-C, a cache hit returns in around 300 microseconds, well under a millisecond. For a high-frequency trading or gaming workload, that's the difference between feasible and impossible. This is why gaming leaderboards and real-time bidding systems lean on DEA-C. They need consistent sub-millisecond reads, and they're happy to accept eventual consistency to get them. Secondary indexes come in two flavors, and the exam tests the difference relentlessly. On the left, the global secondary index, or GSI. You can add a GSI anytime after the table exists. It can have a completely different partition key from the base table. It gets its own provisioned throughput, and it only supports eventual consistency. On the right, the local secondary index, or LSI. It must be defined at table creation. You cannot add one later ever. It shares the base table's partition key but uses a different sort key. It shares the base table's throughput, and crucially, it supports strongly consistent reads. Think of an LSI as a chapter index inside a book. It has to be built when the book is printed. A GSI is more like a separate card catalog you can add to the library whenever you want. This is the pattern the exam writers love. They describe a production table that's already in use, and they say the team needs a new query pattern that requires an index. The answer is always a GSI because an LSI cannot be added after the table exists. That's it. Same scenario, different wording, dozens of variations, but the answer key never changes. Memorize this one sentence, and you'll get the question right every time. Two capacity modes, and the exam decision is straightforward. On the left, on demand, you pay per request, the table scales instantly, and it's the right choice for spiky or unpredictable traffic, or for a new application with no usage history. Amazon Web Services has significantly reduced on-demand pricing in recent years, which makes it more attractive than it used to be for steady workloads too. On the right, provisioned with auto-scaling. You reserve a baseline of read and write capacity units. You pay for what you reserve whether you use it or not, and auto-scaling tunes within your minimum and maximum bounds. Provision still wins on cost for steady, predictable workloads. The exam pattern is simple. Words like spiky, unpredictable, unknown, or new application, pick on demand. Words like steady, predictable, or cost optimization with known traffic, pick provisioned plus auto-scaling. Before we wrap up, lock this list into memory. If you see any of these words in a question, analytics, aggregations, joins, business intelligence dashboards, ad hoc queries, or reporting, eliminate DynamoDB from your options immediately. It doesn't matter how cleverly the question describes the workload. DynamoDB has no joins, no group by, no ad hoc SQL. The right answer for those questions is Athena for serverless querying, Redshift for warehouse scale analytics, or Glue and Spark for heavy transformations. This one filter alone will save you points across multiple questions on exam day. Here's the rapid-fire decoder. If you see hot partition or write throttling, the answer is random suffix write sharding. Spread those writes across many logical keys. If you see change data capture to Lambda or S3 with under 24 hours of retention, the answer is DynamoDB Streams, which gives you ordered item level change events. If you see auto-delete expired items at no cost, the answer is TTL, and remember it runs within a few days, not instantly. If you see microsecond reads with no code changes, the answer is DEA-C, not ElastiCache, because only DEA-C is API compatible with DynamoDB. And finally, if you see add an index to an existing table, the answer is GSI, never LSI, because LSI cannot be added after table creation. 5 patterns, 5 answers. That's most of what DynamoDB will throw at you on the exam. 7 things to lock in. 1. DynamoDB is for OLTP point lookups, never analytics or joins. 2. The hot partition fix is appending a random suffix between 1 and 200 to spread writes. 3. Streams gives you time-ordered item-level change data capture with 24-hour retention. 4. TTL deletes expired items for free, but within a few days, not instantly. 5. DEA-C gives microsecond reads, is a PI compatible and eventually consistent only. 6. GSI anytime, LSI at creation only. 7. Spiky traffic picks on demand, steady picks provisioned with auto-scaling. Get these right and DynamoDB becomes free points on the exam. Alright, let's test what you've learned. Question 1. A Nexer retail table stores clickstream events with the partition key set to the current date. The team is seeing provisioned throughput exceeded errors during peak hours, even though the table's total capacity is far from exhausted. What's the correct fix? Is it A. Increase the table's provisioned write capacity units? B. Switch the table to on-demand capacity mode? C. Append a random number between 1 and 200 to the date partition key? Or D. Add a global secondary index on the date column? Take a moment to think about it. The answer is C. This is the classic hot partition scenario. Every write today hashes to the same partition, so you hit the per partition limit of 1000 WCU no matter how much total capacity you've provisioned. Adding a random suffix shards writes across 200 logical keys, spreading them evenly across partitions. Question 2. A data engineering team needs to replicate every insert, update, and delete from a DynamoDB table into an S3 data lake within minutes. The downstream Lambda function must process changes in the order they occurred. Which solution requires the least operational overhead? Is it A. Enable DynamoDB Streams and configure Lambda as a trigger to write to S3? B. Schedule a nightly glue job to scan the table and write changes to S3? C. Use a WSDMS with DynamoDB as the source and S3 as the target? Or D. Enable DEA-C and configure it to write through to S3? Think it through. The answer is A. DynamoDB Streams captures time-ordered item-level changes, and Lambda integrates natively as a trigger. This is the textbook change data capture pattern. A nightly glue job misses the minutes latency requirement, DMS adds infrastructure overhead, and DEA-C is a red cache. It doesn't write to S3 at all. Question 3. An application reads from a DynamoDB table millions of times per hour. The team wants to reduce read latency to microseconds with minimal changes to the application code. The application uses strongly consistent reads for financial transactions and eventually consistent reads for product browsing. What should the team implement? Is it A. Add DEA-C in front of DynamoDB? Both read types will see microsecond latency. B. Add DEA-C in front of DynamoDB, only eventually consistent reads will benefit. C. Replace DynamoDB with ElastiCache for reads. Or D. Add a global secondary index to speed up reads? Pause and think. The answer is B. DEA-C is a PI compatible and gives microsecond reads, but it cannot serve strongly consistent reads. Those requests bypass the cache and hit DynamoDB directly. So the product browsing reads will see the speed up, but the financial transaction reads will not. Knowing this caveat is exactly what the exam is testing. Question 4. A production DynamoDB table has been running for 6 months. The analytics team now needs to query the table by a new attribute that isn't the partition key or sort key, and they need strongly consistent reads on this new query path. What should the engineer do? Is it A. Add a local secondary index on the new attribute? B. Add a global secondary index on the new attribute? C. Recreate the table with a local secondary index defined. Or D. Use Athena federated query to scan the table. This is a tricky one, think it through. The answer is C. This is a trap question. LSI supports strongly consistent reads, but it must be defined at table creation. You cannot add one later. GSI can be added anytime, but it only supports eventual consistency. Since the requirement demands both strongly consistent reads and the table already exists, the only way to satisfy both is to recreate the table with the LSI defined upfront. Last one, question 5. A team needs to run ad hoc SQL queries with aggregations and joins across a DynamoDB table and historical S3 Parquet data. The DynamoDB table holds active orders. Which approach is correct? Is it A. Run the analytical queries directly against DynamoDB using partiql, B. Migrate the DynamoDB table to Redshift and query there? C. Use Athena federated query to join DynamoDB with S3 Parquet? Or D. Add DEA-C to DynamoDB to make the analytical queries faster? Final answer time. The answer is C. Two rules collide here. DynamoDB is wrong for analytics with aggregations and joins, so options A and D are out immediately. You don't migrate a live operational table just for ad hoc queries either. Athena federated query lets you join real-time DynamoDB data with historical S3 Parquet in a single SQL statement. That's exactly the exam-correct pattern. And that's a wrap on Amazon DynamoDB for data engineers, streams, TTL, DAX, and key design. If this helped you out, smash that like button and subscribe for more. See you in the next one.